السلام عليكم ورحمة الله تعالى وبركاته. I'm Salma Al-Mahdi, and in this fourth lecture we are going to discuss metabolism of unsaturated fatty acids and eicosanoids. By the end of this lecture, students should be able to identify essential fatty acids, state the significance of essential fatty acids in the synthesis of eicosanoids, identify enzymes of that synthesize unsaturated fatty acids, and to discuss the oxidation of unsaturated fatty acids, and to outline the synthesis of prostanoids, and finally discuss biomedical relevance of essential fatty acids, unsaturated fatty acids, and prostanoids. Compared with plants, animals have limited ability to saturate fatty acids, and that is why we have to take, as humans, we have to take essential fatty acids in our diet, and we need them because they give rise to eicosanoids, the 20 carbon atom compounds, as you know from your lipid chemistry: prostaglandins, lipoxans, leukotrienes, and lipoxygens. Essentiality corresponds to the ability to introduce double bond in a specified position in the fatty acid. Mammals in general can synthesize or can make double bond at delta 4, delta 5, 6, and 9, but they cannot introduce a double bond beyond delta 9. So anywhere here between the carboxy terminus and the 9th carbon atom, mammals, including humans, can introduce double bond, but beyond that they cannot. In contrast, plants can do that. They can introduce double bonds here, 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 anywhere up to the omega carbon or proximal to the omega carbons. And the essential fatty acids, as you know, are linoleic acid, omega 6, arachidonic acid, omega 6, and the omega 3 alpha linoleic acid. Here are examples of non-essential unsaturated fatty acid: palmitoleic, 16 carbon atom, and oleic acid, and 18 carbon atom. Also, both of them are delta 9. The essential fatty acids are linoleic acid, which is an omega 6, arachidonic acid, which is an omega 6, and the alpha linoleic, which is omega 3. Arachidonic acid here is an asterisk attached to it to signify that it is not essential in all mammals. It is particularly so for cats. Synthesis of unsaturated fatty acids occurs in several tissues, including the liver. It starts as a substrate for the synthesis of monounsaturated fatty acid. It is, of course, unsaturated fatty acid. We have seen how the body synthesizes palmitate residue, SR residue. So it will take one of these saturated residues and desaturate it using a desaturase enzyme. And it almost always the first double bond to be introduced into the newly synthesized monounsaturated fatty acid will be a delta 9. This desaturase enzyme is present in the endoplasmic reticulum. It contains non-heme as a coenzyme. It requires NADH, molecular oxygen. It also needs cytochrome B5 as a mediator for electron transfer. This cytochrome B5 can be free or it can be part of the desaturase itself. So, for example, stearoyl-CoA here is saturated delta 9. Saturated 18 carbon atom compound we need to introduce, or the body wants to form a monounsaturated fatty acid from this substrate. Delta 9 desaturase will introduce a double bond here at this position from palmitoyl-CoA. Also, a double bond will be introduced at delta 9 position. How does the body synthesize polyunsaturated fatty acid? It will also use the disaturase in addition to an elongase. So the desaturase will introduce the new double bonds. The elongase will elongate the fatty acid side residue to carbon atom at each time. The new double bonds will be methylene interrupted in between them. There will be methylene groups. And the site of introduction of the new double bond in high animals, it will be between the existing double bond and the carboxy terminus. Because we said that, we have already mentioned that the mammals and high animals cannot introduce a double bond beyond 9 position. So any new will be between the carboxy terminus and the 9th carbon atom. While plants can, of course, it anywhere act as omega carbon. Animals can synthesize oleate family, omega-9 by the combined action, as we said, of desaturase and elongase. However, they cannot desaturate it beyond delta 9. So the omega-6 family from linoleic and omega-3 family from linolenic acid cannot be synthesized in the body and must be provided in the diet. So, in the body, oleic acid and saturated fatty acid can be used to create an omega-9 family by a delta 6 desaturase, which will introduce a second double bond, elongase. It will convert 18 to 20 carbon fatty acids. Then a delta 5 desaturase will introduce a third double bond, and then an elongase will convert a 20 to 22 residue, another chlorophores, third fatty desaturase to introduce a delta 4 to have 8022 carbon atom fatty polyunsaturated fatty acid with 4 carbon atoms. This can easily occur in the body. But because the body cannot introduce delta 9, they will have to start from dietary linoleic and dietary alpha-linolenic acid. Likewise, a desaturase will be used to introduce double bond, while elongase will be used to elongate the residue. If the body doesn't want more double bond, just elongation, elongase can be used as well. So the omega-9 family from oleic, as we said, it has a double bond at 9. No new bond will be introduced. No new double bond will be introduced here, and the body cannot do that. But between the existing delta 9 and the carboxy terminus is where the addition of the new double bond will take place. Likewise here, in the omega-9, the omega-6 family, this is a delta 9 position. The new double bonds will be introduced between the carboxy terminus and the delta 9. Synthesis of arachidonic acid, as we said, arachidonic acid is semi-essential, sort of, because cats as a mammal and as animals cannot synthesize it. As you know, arachidonic acid is an Eicosa tetraenoic acid, meaning Eicosa, it has 20 carbon atoms, tetraenoic, it has 4 double bonds, particularly at delta 5, 8, 11, 14. The body can synthesize arachidonic acid from linolenic. Cats cannot synthesize arachidonic acid because they lack the delta 6 desaturase, so they must take arachidonic acid in their diet. The nutritional requirement for arachidonic acid for animals that have the enzyme delta 6 desaturase can be arachidonic acid can be dispensed with or no longer needed if linolenic is present, because the body can use linolenic to synthesize arachidonic acid. And your first question for today is, what is peculiar about the metabolism of unsaturated fatty acids in cats? I have already mentioned 2 points. I would like you to add more. To synthesize arachidonic acid, first linolenate has to be activated to linolyl CoA. As we said, CoA means this molecule is active and ready now to proceed for further reaction. And then a delta 6 desaturase will require, as we said, molecular oxygen in ADH to introduce this double bond at position 6 at delta 6, counting of course on the carboxyl terminus. And then in elongase, we'll add 2 more carbon atoms, so instead of 18, now we have 20 carbon atoms. Of course, the numbering, as you can see here, the double bond numbering has changed from 6, 9, 12 to 8, 11, 14. And then a D5 desaturase will introduce a double bond at delta 5, so it will be 1, 2, 3, 4, 5 will be introduced here. So this is a new double bond. 1, 2, 3, 4. Now we have 4 double bonds. It is tetraimine, and we have the 20 carbon atoms, so it is an icosanoid CoA. The biomedical relevance of essential fatty acids is that the deficiency is rare and not fatal and reversible. So even if it occurs, it can be reversed by supplementation of essential fatty acids. It can be encountered in premature infants and in those who are on parenteral nutrition. It has skin manifestations in the form of dermatitis, alopecia, and hematological manifestation in the form of thrombocytopenia, and intellectual disability, particularly in children, because they are growing up and their brains and nervous tissue needs these polyunsaturated fatty acids. Non-essential polyenoic acids of the omega-9 family will replace, of course, essential fatty acids in complex lipids and membranes. Remember the name DHA and EPA. DHA, docosahexaenoic acid, and EPA, eicosapentaenoic acid. You will come across them as supplements. So on prescription for essential fatty acid, the supplementation of essential fatty acid. These are the ones that will be provided. Deficiency of docosahexaenoic acid can lead to retinitis pigmentosa, which is an inherited eye disease due to degeneration of roots, that will lead to various degrees of vision impairment. Here is a normal retina, and here is a retinitis pigmentosa. You can see the darkest dots refer to the degenerated areas of the retina. Low omega-3 index is associated with increased risk of coronary heart disease, and dietary consumption of essential fatty acid DHA and EPA is associated with decreased incidence of inflammatory disease, and the beneficial effects are subject to so many research that I would like you to check this paper. It's very interesting study that has been done in Sudan, and the population studied were sickle cell anemia patients. And, they were provided with it was double-blind placebo controlled randomized controlled study in which omega-3 was provided to children. The main finding of the study is that the anti-aggregatory, the anti-adhesive, the anti-inflammatory, and vasodilatory omega-3 fatty acids are significantly reduced in patients with sickle cell disease. And supplementation, those with supplement have fewer hospitalization, less need for blood transfusion, and less complication. Please check it. Now we have finished discussing synthesis of mono and polyunsaturated fatty acids. So how does the body oxidizes those unsaturated fatty acids? It uses a modified method oxidation, and we say modified because at certain point beta oxidation cannot proceed when it encounters cis double bond. The enoyl CoA hydratase enzyme of beta oxidation acts only on trans bond. However, in polyunsaturated fatty acid we have cis double bond, so it will not be able to act on it. What happens is that we'll take an example here, oleic acid. If the body decides to oxidize oleic acid, will have to be first activated on UAA by addition of OA. And then it will start with 3 cycles of beta oxidation. There is no problem regarding this part of the fatty acids. So 3 acetyl CoAs will be produced, and the enzyme machine design will stop here because this cis double bond is not accessible. The result will be 3 acetyl CoA molecules and a dodecaenoyl CoA. Dodeca meaning it is 12 cis. The delta 3 bond is in the cis configuration. The body will need an isomerase to isomerize the cis delta 3 dodecaenoyl CoA to a delta 3 delta 2 enoyl trans delta 2 dodecaenoyl CoA. So from a cis to a trans configuration. This then enoyl CoA hydratase will proceed, followed by dehydrogenation, and then cyanolytic cleavage. Cyanolysis will release acetyl CoA and the decanoyl CoA, the carbon atom, which will be subject to 4 cycles of beta oxidation. So the total amount of acetyl CoA produced will be 3 from the beginning, 1 here, and 5 from the 10 acyl residue. A second example that was a monounsaturated. Now we need to illustrate oxidation of polyunsaturated fatty acid using linoleic acid as an example. It is also activated first to linoleal CoA. It will also undergo 3 cycles of beta oxidation normally, and then it will stop the enzyme to stop at this cis double bond. We need the isomerase to convert the cis to a trans delta 2. This will be followed by hydration, dehydrogenation, and pyrolysis. And then the first dehydrogenation of beta oxidation can proceed. And then we need reduction and isomerization. And then the cycle of beta oxidation, hydration, dehydrogenation, cyanolysis, and ending up with an octanyl CoA. And this decaoctanoyl CoA will proceed by cyanolysis to release an acetyl CoA and octanyl CoA. Then we undergo 3 cycles, multiple cycles of beta oxidation. Regarding metabolism of eicosanoids, let us refresh our memory regarding what do we mean by eicosanoids. They are physiologically and pharmacologically active compounds, as we said, include prostaglandins, antioxidants, lipid and lipoics. They act as local hormones, so they will act in the nearby vessels. They will elicit their biochemical effects via decoupled protein receptors. Eicosanoids have 3, we group them into 3 categories. Each comprise mainly a prostaglandin group, isoamboxan group, and leukotriene group, possibly iboxine, but these are the main 3. And they are synthesized from, of course, eicosanoic acids, these are 20 carbon atom unsaturated fatty acids, from the essential fatty acid linoleic and then alpha-linoleic acid, or can be directly from the dietary arachidonate and eicosanoid beta-amide. So this is linoleic. It can be used to synthesize group 1 prostanoids and leukotrienes. The diet or coming alpha-linoleic and arachidonate dietary can arachidonate for group 2 and linoleic for group 3. The cyclooxygenase and lipoxygenase pathways act on arachidonate, that's part of membrane phospholipids. Phospholipase A2 will release arachidonate, and then arachidonate can proceed via either pathway either through a cyclooxygenase to produce prostaglandins and thromboxans, or through a lipoxygenase pathway to produce leukotrienes and lipoxygens. How are prostanoids synthesized in the body? Prostanoids mean prostaglandin, thromboxan, and prostacyclin. That is prostaglandin I2. Each cell type produces only one type of prostanoid, so it will be specialized in production of one line or one type of prostanoids. Prostaglandin synthase has two isoforms, prostaglandin H synthase 1 and 2, and each isoform has two enzymes. So in total, we have four enzymatic activities, but two cyclooxygenases for each one cyclooxygenase for each isoform. So we have a COX-1 and COX-2, one for each isoform. The cyclooxygenase pathway produces prostaglandin H, and prostaglandin H then is a paired molecule that can give rise to prostaglandin D2, E2, F2, and etc. Prostanoid synthesis can be switched off either by self-destruction of the enzyme itself, it is called a suicide enzyme, or it can be inactivated by 5-hydroxy prostaglandin dehydrogenase, which can be blocked by sulfasalazine and indomethacin. So drugs can lead to switching off or stopping or inhibition of synthesis of prostanoids. And these, of course, logically they act as anti-inflammatory, because those prostanoids are inflammatory molecules, enhance inflammation in addition to other physiological effects. So when we introduce drugs that block their synthesis, the end result will be less inflammation, and this in here we have isodonate by cyclooxygenase, leading to synthesis of prostaglandin G2, and then the rest will come from it by different pathways, either isomerases, reductases, and other syntheses. Please note here the site of action: aspirin, indomethacin, and eicosanoids it at the level of a cyclooxygenase. Imidazole here at the level of thromboxan synthesis. The biological relevance of prostanoids is this drug action on the enzymes for their synthesis. Aspirin inhibits both cyclooxygenase 1 and 2 by acetylation, and this is an irreversible type of inhibition. And that is why aspirin, in addition to indomethacin and ibuprofen, are all called non-steroidal anti-inflammatory drugs. Indomethacin and ibuprofen inhibit the cyclooxygenase by competition with the substrate arachidonic. Corticosteroids, a different group of anti-inflammatory, inhibit transcription, so they act as a kinetic level. They will inhibit transcription of prostaglandin H synthase to isoform 2. Your second question for today is: how are the desirable and undesirable pharmacological effects of aspirin are related both to cyclooxygenase? So the cyclooxygenase will derive as a desired pharmacological effect. It also can cause undesirable side effects. So how is it responsible for both the good and the bad? And your third question is: why do Greenland Eskimos have low incidence of heart disease, diminished lipid aggregation, and prolonged coating? Since of leukotrienes are family of conjugated trienes, and they are produced, they have immunological effects, and they are produced in immunologic and non-immunologic stimuli in cells such as leukocytes, mastocytes, macrophages, immune cells, and platelets as well. They are synthesized from eicosanoic acids by a 5-lipoxygenase. So cyclooxygenase is synthesis of prostaglandins, and lipoxygenase of cells and lipoxygenase of this leukotriene. The first leukotriene to be synthesized, or the parent one, will be leukotriene F4. Lipoxygens are a family of conjugated proteins present also in leukocyte, formed by a combination of more than one lipoxygenase, and these are the pathways for the lipoxygenases. Of leukotrienes. The biomedical relevance of leukotrienes and lipoxygens is that they are both potent regulators of many inflammatory and allergic diseases, including asthma and allergic rhinitis. They were used to be called slowly acting substances for anaphylaxis, particularly leukotriene C4, D4, and E4. They are very potent inflammatory molecules. In fact, they can be 100 to up to 1,000 times more potent bronchoconstrictors compared to histamines and prostaglandins. So they constrict the bronchi, they narrow the airways, and that is why they will be responsible for the manifestation of allergic diseases such as here in this example, bronchial asthma, where the narrowing of the bronchi will lead to sensation of chest tightness. Leukotriene receptor antagonists, such as multi-locast, they will use to block the receptors for leukotriene. So leukotrienes will not be able to act because the receptor will be already occupied by the antagonistic drug. These drugs will have an anti-inflammatory and anti-allergic effect, and the multilocast is used in the treatment of both allergic rhinitis and allergic asthma as a prophylactic agent. In this graph here, you can see that the clinical manifestation of the immune response, and this here is an allergic response as polluted against hours after allergen exposure. At 0 time, there is nothing, and then after exposure, the first released inflammatory mediator will be histamine in the first hour. Then it will start to go down, after which other mediators will rise up, will be produced by the cells, particularly our slow reacting substances of anaphylaxis and leukotriene C4, D4, and E4. This can be blocked, of course, by the multilocast and similar drugs. Histamine is rapidly appearing here because histamine will be already formed in the immune cells, in the mast cells, and in the basophil. It will be kept in vesicles, and it will be released as soon as the immune cell and allergic immune cell recognize the allergen. However, those will take time to appear because the start will synthesize them from the scratch after allergen exposure. And that is why the manifestations of asthma, in the management of asthma, we have to tackle both the rapidly released substances, mainly the histamine, and the late released substances, leukotrienes. And the management has to encompass both those types of molecules. Thank you very much. See you next time.